No, we were all standing around drinking last night, having a good time. And I
Hold
was
on, hold on.
talking to Roshan, and he explained to me how to pronounce his name. And I was feeling pretty confident about it last night when we were talking, and I'm not feeling so good about it anymore. So I think we'll just introduce him as Roshan, and he's going to be presenting the paper Users Are Closer Than They Appear. He is a final year PhD student at UCSD, advised by Professor Dinesh Bharadia. His research expertise is developing deployable wireless sensing and localization systems, and he's currently on the academic job market. So I'll
Yeah.
turn over the floor to you, sir.
Can you guys hear me? Great. Yeah, thank you for the introduction, Neil. And yeah, if anyone wants to know, it's pronounced Ayalasomi Ajula, that it being out there. So yeah, thanks for the introduction. Yeah, I'm very excited to talk to you guys about our work on user device location, privacy preserving algorithm that we have developed. So over the past few years, I myself have worked extensively on localization systems, where we have developed systems that can locate users passively to accurately up to decimeter level accuracy. Like you can locate yourselves within a couple of chair distance in this conference room, for example, right? So over time, I've come to realize that this is a beast I've created, and I have to see, and anyone can use the system to invade privacy of any user, right? And so that's where we tried to look into a solution for this system, for these localization systems, and that's where we present our work, Mirage. Um, so yeah, like I said, over the past few years, the localization systems have come down from being meter level accurate using signal strength based systems to being decimeter accurate, where you can locate one in, at least at a room scale level, right? And this mainly was because of the academics who have started hacking into these Wi-Fi chipsets to get information that can enable location estimates. And further, looking in, because of the interest in these systems, now companies have also started open sourcing these location estimation parameters to the application layer, like Qualcomm and Quantum have started doing this. And using these systems, now there are companies that actually have started providing location as a service out there, like Cisco DNS Spaces and Juniper Networks, right? And now these are out there, right? And because of this being out there, there are few there are few instances where, for example, in this specific case, a retailer was tracking the users without their explicit consent using these systems, right? And so now this is an important problem to be solved. We need to ensure that the location is being provided to only the authorized users and not for anyone and everyone, right? And so let's consider how this attack model is happening, right? Let's say the user is going to an enterprise network. They're connecting, there are multiple access points in this network, right? They can connect to any one of these access points as they're moving around based on the signal strength and the connectivity that they have. And let's say for in this specific scenario, they're connected to access point 1, right? And in this specific scenario, let's say these access points are now compromised because there's for example, in the retail market scenario where the retailer has set up these access points and are tracking the user in the backend, right? Now, how do they get the user location in this specific scenario, right? Let's first understand that, right? So a simple way to do that is first they can estimate the range or the distance of the user using the existing 802.11mc protocol, IEEE protocol, and this will give decent enough accurate range estimates. And there are a lot of accurate angle of arrival prediction algorithms out there like Spotify and Music that can give you the direction of the user. And now using both range and direction, you can predict the user location here. And so we want to protect against this kind of an attack, right? And that's where we present our work, Mirage, where without Mirage, when the spy queries for the user location, they get accurate user location when the Mirage is not turned on a smartphone. And for example, if you have the smartphone and you have turned on Mirage on the system, using Mirage, now the spy will actually be tracking an incorrect location of the phone, and so that's the Mirage part of it, where it's basically tracking ghost of the smartphone image. And so to understand how we develop Mirage, let's see what are the requirements for these kinds of systems. Firstly, we should be able to robustly obfuscate the location where the attacker should not be able to get any residual information left in the estimates that measurements that they're using to do the location estimates. And this obfuscation of the location should not compromise the existing communication link, because you still want to be connected to the internet. For example, if you are in an Airbnb scenario where the owner has set up a malicious Wi-Fi access point, but you still want to be connected to the internet when you're going to the Airbnb, staying at the Airbnb, right? And finally, the attacker should not be able to decode the location of the user, even with the knowledge of the implementation of Mirage, right? And so, yeah, these are the basic requirements that we set up for Mirage, and we designed Mirage based on aim to solve these three specific requirements. And before we understand how Mirage exactly works, let me quickly give you a brief idea of how localization actually works, and what are the actual problems that we can use here out there. Right. So here in this specific example, the user is now talking to the access point, right? Because the user is broadcasting the signal can go in multiple different directions. One of them would be the direct path, which is marked in green at an angle theta d, and the other would be the reflected path, which is at an angle theta r, shown here. And to have a more visual representation of the same, we have converted the measurements at the access point into this image, where in this likelihood image, where basically on the x-axis is the distance, and on the y-axis is the angle of arrival, right? You can see that the higher the pixel intensity, the more likelihood that the access point thinks that the user is along one of these two locations, right? But there are these two different locations now that the user could be at. How would any system identify which would be the correct location of the user? And the most fundamental understanding here is that direct path always travels the least amount of distance. So you can identify the first peak that's occurring in this image along the distance axis, and identify that as your direct path, and predict the distance and angle for that specific path. So that's how you could do the localization for any of the existing systems, right? So if we can somehow make sure that the attacker does not have access to the direct path, then we have solved our problem, more or less, right? Like, then we can actually avoid being located by the attacker. But how can we ensure that, right? How do we do that? So one simple way is to just say, hey, I'm not going to transmit along direct path at all. I'm just going to create a null along that direction, and I'm just going to focus all my energy or beamform in the angle along the reflected path direction. But the problem here is you're removing one of the most dominant paths in the environment that you're using to connect to the network. So basically, you're reducing the signal-to-noise ratio, and thus you're actually compromising your communication link to the access points as well, right? So how do we get about it? Like, how can we remove this direct path or obfuscate this direct path? And that's where we present our work for our idea of Mirage, where, for example, so we are measuring these physical parameters of theta d, dd, which are the angle of arrival and angle of arrival and distance for direct path, right? Which are the physical measurements of the space. But if somehow we can add some information to the signal that the physical representation changes, that the direct path travels more distance than the reflected path, which is dd plus d obfuscation here is more than dr, then basically we can overcome our problem, because now the attacker is going to predict the first path to be the reflected path, and so they're going to predict the user distance to be dr and user direction to be theta r, both of which are incorrect. And so thus we can actually obfuscate the actual user location, and this is what we exactly do in Mirage. We do this by performing some beamforming by designing a beamforming matrix that can be applied to the data transmitted out. There are further technical details in the paper that I will let you guys go back and read. And thus, the direct path is no more the least traveled path, which actually obfuscates the user location, right? And this creates a mirage of the user's accurate location, because now the user is actually somewhere else, almost on the other side of the room. So now to understand how exactly what is the exact minimum amount of obfuscation distance that you need to add, how do we get this estimate? We can see that this is the scenario we have, where we have the distance measurement, which is dd plus delta d. The delta d comes from the timing offsets between the access point and the user, because both of them are running on two different clocks. they have different phase synchronization, they have different frequency and time synchronization offsets, which causes for these delta D error in the distance, right? And because you're transmitting reflected path also originates from the user. It also has the same delta D offset. Ideally, we see that DD plus delta D is less than DR plus delta D there, right? Which is basically the direct path is shorter than the reflected path. But what we want to do is make sure that deobfuscation, when you add deobfuscation, it actually becomes that direct path is longer than the reflected path. So at the end of the day, what we want to so the way we can actually extract the minimum amount of deobfuscation is to get the relative distance between the direct path and relative path in the figures that we have seen earlier, right? So, but we also don't want the attacker to be able to identify the obfuscation. Like, let's say, if the attacker knows that mirage has occurred, then they could always say, hey, I'm gonna predict second path or something, and then get the accurate user location, right? So we don't want that to happen. And so to avoid that, we sample the deobfuscation distance from a Gaussian distribution whose minimum cutoff is at dr minus dd, such that you're always adding a minimum of dr minus dd offset and more than that. So now each time the attacker queries for location, there is a different amount of offset added to the direct path, and so it is going to be one of the n multipath, but not just the second multipath in the environment. And yeah, so this is how we have implemented Mirage. This is a quick demonstration of, we have seen these images, I've shown you these same images through and through, where this is the first without a Mirage being deployed. You can see that the direct path is at 0 meters at minus 30 degrees, while reflected path is 30 degrees here. And with nulling, you can see that there is only one path at 6 meters at 30 degrees, which is just the reflected path. But you see that there is a 6 dB of reduction in the SNR, and then that's basically compromising the communication link there. And finally, with Mirage, we see that the signal strength is almost the same, and so it's not compromising your existing communication link, but you have the direct path actually now occurring after reflected path. To be exact here, 9 meters after the reflected path. So now you cannot, if the attacker tries to query for location, they're going to get that the user is at relative distance of 0 meters and at 45 degrees, which is going to be a very incorrect location. While I've demonstrated Mirage, there are some past works, like the MAC randomization work, but it was shown that it could be easily broken. There are also some range estimations like the 802.11mc protocol, but recently we have seen that there are some, like YPEEP has shown that you can actually attack to reveal 802.11mc range estimates. There are other signal strength and wireless environment modifying systems, but all of them start to break the ongoing wireless communication by compromising the signal to noise ratio of the existing connection. So in contrast, we have seen that Mirage actually obfuscates the user location, right? You cannot get user location anyways. And it also maintains the communication link. We are not breaking down, we are not removing any of the existing paths, so the communication link is still strong and it's not compromising any of the existing communication links. And even with the knowledge of the Mirage, attacker will only know that the real location would be one of the n multipaths in the environment, but wouldn't know which of them is the actual correct path. So they are still confused about them. And yeah, while I've demonstrated Mirage and how it has actually achieved the requirements I've said earlier, this is only the first step, and there are further open problems and challenges in this field of location privacy. Firstly, while you have tackled an enterprise network, there might be a case where the attacker deployed a few passive sensing access points. And since the user is just broadcasting the signal, these access points can passively listen and use that information to triangulate the user from multiple vantage points. And thus, there is a need for a system to be able to defend across multiple of these access points simultaneously, and not just with one access point. Additionally, we have set a requirement that the attacker should not be able to predict the user location under the knowledge of Mirage, right? Which means that the measurements made at the access point should not have any residual location information that can indicate user location to the attacker. But there are few scenarios, even in Mirage, where Mirage could possibly reveal the actual user angle of arrival if the attacker knows Mirage's implementation, where the attacker can see a residual or a ghost. You can see the residual multipath marked in red. That is created, which can aid the attacker in figuring out which of them is the direct path and which of them is the multipath. And so using this, then basically using this information, the attacker could actually potentially predict actual direct path information, and that would be a problem as well. To understand why this happens before we can solve this, and let us see how each path is transmitted in Mirage, right? From the user's beamforming end, the direct path has this specific beamforming pattern where you can see that the direct path is being transmitted along 0 degrees in this specific scenario. And on the other hand, the reflected path is transmitted along 30 degrees, minus 30 degrees. And on the Wi-Fi access point, they are received at plus 30 degrees, minus 30 degrees and plus 30 degrees for the direct and reflected path correspondingly, right? And so the problem, where does this additional ghost multipath come from, right? If you see, there is one more, there is some leakage of energy along minus 30 degrees in this specific beam pattern for the direct path. And this is where the additional leakage and the additional path comes from, right? This is where you can see the ghost multipath. It's around minus 30 degrees as well, and is also obfuscated by similar amount as the direct path. And this is because the direct path's beamforming vector there is obfuscated, which is transmitting two signals, one along the 0 degrees, the other along minus 30 degrees, which is creating an additional path as well. And thus, we need to also design a system that can actually, while beamforming across these two directions, the two beamforming vectors should also be in the null space of each other, so that they're orthogonal and do not have these leakages in the corresponding direction that we're beamforming. So, and finally, while in the current Mirage setup, we consider user to be quasi-static, that is, for the instance of user localization and obfuscation, which are on the orders of a few milliseconds, we assume that the user's motion is negligible. But there are some interesting problems of dynamic multipath environments where either the user device is moving or fast enough to change the multipath environment, or the environment itself has some dynamic reflectors like people moving around. So we need to model the dynamic multipath of the environment to be able to accurately obfuscate user location as well. And yeah, so this is how I'll leave you guys with the conclusion of Mirage, where what are the current achievements and what are the future challenges and open problems. Please feel free to contact either one of the authors. All three of us are co-primary authors, and yeah, you have the QR code to scan for the paper. Thank you.
I'm Nakul from UMD College Park. Great talk and even exciting work. My question is something related to the corner case that you've talked about. So that talks about a single Wi-Fi access point trying to get two angle of arrivals direct and multipath and then locate. What are your thoughts on different access points, all getting the AOA of the user and then triangulating it, so they don't no longer read the range information, it's just angle of arrival? So
yeah, I think that's one of the future work, like I mentioned. We would need to try and obfuscate for each individual access point as well, which would need that you are basically removing the direct path for each one of them. And that's a challenge in itself, because passive sensing is just like you are broadcasting. You cannot avoid broadcasting in general, or you just make sure that you are only talking to one of the access points and direct all of your energy towards that access point, so that none of the access points have any signal that's being received. But yeah, if your access points are hidden even in those scenarios, that will be a different challenge as well that we should look into as well.
I have a follow-up. So that's one of the ways, and it's great like if you could null all the other ones and just beamform to one. But is there some way, like I believe to extend the de-obfuscation, you added some latency to make it think like it's far away.
Yeah.
Is there some way that you could make the access point think that it's at a very different angle? Instead of just nulling it out, we can transmit it in some way, like that the receiver, I know it's hard because the physical layer will get that phase information, but what are your thoughts on this?
Yeah, I think at that point it is a battle of number of antennas each of them has, because the more antennas you have on the access point, if they are more than they are on the phone, they can always decode your information, and so that's basically at that point battle of diversity that you have on the access point or on the smartphone, and yeah.
Thank you for this interesting presentation. So I have a question with two parts. The first one is how you will be able to know a priori the line of sight, especially in the mobility, when you have a certain mobility actions and happening in your environment, how you can predict that this path is going to be my line of sight.
Yeah, so these transmissions are around the order of microseconds. So for that specific instance, we are assuming that the user is quasi-static, so they are more or less static.
Okay.
And we are assuming back and forth communication continuously happening, and so we are actually measuring the channel on the downlink, not on the uplink, and we also assume that there is a channel reciprocity happening. There is channel reciprocity holds, and so we use the downlink channel measurements to understand what are the directions of the direct path and the reflected path.
I see. And what's going to happen if you don't have this line of sight?
Then, well, the access point itself cannot locate you accurately. They need more information regarding the environment of where the reflectors are and whatnot to understand where the user could be, and that's a very hard problem to model for sub-6 GHz at least.
Okay, thank you.
So aren't these problems kind of better addressed by regulation and things like that? You're kind of going after a case where you're not trusting the provider of the device and they're misusing the data. So fundamentally something is broken, and that's what needs to be fixed, because you're going into a level where you may not have access, or most users absolutely have no understanding of how to do this, and you may not have the right controls to insert yourself in these lower levels of the stack. So you have any comments on that?
Yeah, I think as of now, the the chipsets, Wi-Fi chipsets that are exposing these channel estimates to the application layer are not exactly thinking of any security protocols yet. They're just open and out there, and they just provide these channel estimates actually provide very accurate information of the physical surroundings of the environment itself. While they could be protected using protocols, but you could see that even 802.11mc protocol had a hack around it to get range estimates of the user. So it's better to actually make sure that user has a capability that if and when they want to turn off, or not let the access point not know the location while still being able to communicate with them, give them the capability to do that.
So where would you think you'd be able to? Is it a setting on an iPhone?
Yeah, something of that. So like on an iPhone or an Android, you can just simply like you drag down and turn off your location for GPS. You could do something similar to that, where you turn on Mirage and say, hey, now the location is something inaccurate altogether.
Okay.
Hello. I'm not sure if I missed this in the presentation or not, but how far does Mirage obfuscate you, in a room?
Yeah, so I think we did some simulations to that extent, and figured out that on an average for I think 100 different locations across the room spread around in a 10 meter by 10 meter setup, the user location accuracy went off from being sub-metered to all the way being beyond 10 meters. So you're just in a different room or somewhere else altogether.
Okay, that's pretty interesting. Thank you.
All right, folks, thanks so much. Let's thank our speaker one last time. Finally released to lunch. And you can go.